Hi, this is Jurij from Trace Labs, the core developers of OriginTrail. We're excited to share details about our project supported by the ELSA Open Call. In our project, we created a decentralized repository for secure, scalable genomic data sharing and AI-driven personalized healthcare. The primary objective of our initiative is to demonstrate how AI agents can leverage decentralized, privacy-preserving genomic data to assess Alzheimer's disease risk in a secure and trustworthy way. Our project addresses a key challenge in decentralized science: the fragmentation and inaccessibility of data. Despite its value for early diagnosis, precision medicine, and research, genomic data remains locked in silos due to privacy, interoperability, and trust concerns. Now, to solve this, we used the OriginTrail Decentralized Knowledge Graph, a decentralized infrastructure designed to connect structured genomic insights across institutions in a verifiable, secure, and decentralized manner. In our showcase, we simulated a real-world genomic research environment where we used the RNA sequencing data from the Uncode Rush Alzheimer's disease study, where brain tissue samples from affected and unaffected individuals were available, synthetic patient data that includes gene expression, gender, and age to mimic real-world clinical cases, and this data was then distributed across multiple edge nodes on the OriginTrail Decentralized Knowledge Graph, representing a decentralized network of genomic institutions. AI agents then queried those nodes to perform Alzheimer's risk assessment based on federated, verifiable data without exposing any sensitive raw data. Now, the key outcome of our project is a working demonstration of how AI can assess Alzheimer's risk using decentralized genomic data while preserving privacy. Specifically, the AI agent does the following things. It compares a patient's gene expression profile with Alzheimer's related patterns from the RNA sequencing dataset. It generates a personalized risk assessment and provides an explainable report highlighting how and which gene activity patterns contributed to the assessment. This marks a significant step forward in scaling trustworthy, AI-driven healthcare by enabling the following things: structured genomic data sharing across institutions, privacy-preserving data access and analysis, interoperable, semantically rich knowledge integration using the OriginTrail Decentralized Knowledge Graph. Now, this directly contributes to ELSA's objectives by demonstrating how decentralized AI systems can be made trustworthy, explainable, and secure, especially in sensitive domains like health. One of the main challenges we faced was integrating sensitive genomic datasets across distributed nodes in a way that met both privacy and interoperability requirements. We addressed this by doing the following. We used simulated data and privacy-preserving methods to avoid exposing real patient data. We structured data with semantic standards to ensure meaningful querying by AI agents across the nodes and also data interoperability, and also leveraging OriginTrail trusted knowledge infrastructure, which served as the core to guarantee verifiability and provenance of data used by the AI agents. The project has had a significant impact on how we envision decentralized science in healthcare. It proves that it's technically and ethically feasible to connect, structure, and analyze sensitive genomic data at scale without compromising privacy. And moving forward, our goals include expanding this framework to cover additional diseases and datasets, working with healthcare institutions to deploy real-world pilots, and contributing to a global AI-accessible genomic knowledge graph where research and clinical insights can flow securely and responsibly. By unlocking verifiable, privacy-preserving genomic knowledge, we aim to redefine AI-driven precision medicine for the better. Now let's see the solution in action. Hi, so I'm going to show you quickly how the decentralized genomics data repository based on the decentralized knowledge graph could actually work through these prototypes that we've made. On my screen, we actually have three different nodes on the OriginTrail decentralized knowledge graph. One being this personal healthcare AI agent node, and the other two actually representing different genomics data repositories, one being Uncode and the other one we're simulating and calling it Synapse. Now, on these two nodes, so Uncode and Synapse, we actually downloaded from Uncode a bunch of datasets representing datasets with genomic data, which are related and focusing on patients with Alzheimer's disease. And we spread them across two different nodes, simulating two different repositories, so the Uncode one and the Synapse one. And here we can actually see, if we go to the knowledge bank, we can see that we have a bunch of these samples actually here already added to the knowledge bank, meaning that they were transformed into knowledge graph formats. We can actually have a look how this looks like. And what it means is that samples, the gene sequencing samples, they usually come in these TSV file formats. We've generated a simple pipeline that translates them into knowledge graph format. And this is roughly how these gene sequencing samples could look like in knowledge graph format on the DKG. Now, there is also an easy way to actually add additional samples. If we go to contribute, upload an additional sample and create. Oh, there we go. So we can actually add this TSV file, which contains the gene sequencing data, downloaded directly from the repositories online. And what we're doing is actually now transforming it into a knowledge graph format and adding it to the decentralized knowledge graph, where it will then become available as a reference data set for the decentralized healthcare agent, that it will be able to tap into it and use it to do analysis, all of the other cool things related to it. So now what is actually happening is that the knowledge asset is being created on the decentralized knowledge graph, meaning that this sample will become verifiable in terms of the issuer. So we will be able to verify that it was issued by this genomics repository, Synapse in this example. And once the knowledge asset is created, we can actually then go to the personalized AI agent and actually ask questions about this. So, okay, we can see the knowledge asset was created. If we go to the knowledge bank, we can actually see it here. We can open it in the graph as we did before, just so you see how this looks like in knowledge graph form. So this is the sample that we just added. So it's now available on the DKG. And now if we're actually going to the personal healthcare AI agent, we have all of these reference samples from the two different genomics data repositories that are available for personal healthcare agents to actually access and use. But what they would use them with is, if I am now a patient, but then this is my personal healthcare AI agent, what I would want to do is upload my gene sequencing dataset and ask the agent to do an analysis. For example, in this case, as we're focusing on the Alzheimer's patients dataset, I would ask the agent to analyze my gene sequencing data and give me a risk assessment of, how prone I might be to contracting Alzheimer's disease. How we can do this very easily, we have similarly to the sample that we just uploaded before, which is a sample from the data repository, from the genomic data repository. Similarly, we would have a sample once we do our own gene sequencing analysis. So in this case, for myself, this I can then also add to my personal healthcare AI agent. So what will happen here is, now that it's uploading, a similar thing is happening as before when we were looking at the repository, but here it's generating knowledge assets from my personal gene sequencing data, and those will not be made available anywhere. Those are kept completely private on my DKG node, and they're only available to my personal healthcare AI agent, meaning that if somebody else is trying to access them, of course, they don't have access. This is very sensitive data. But the agent, on the other hand, will be able to access the personal knowledge assets that are being created now, as well as all of the reference data samples from these two genomic databases. It will be able to perform an analysis and, in our case, understand the risk or give us a risk assessment for how prone we are to having Alzheimer's disease. So knowledge asset has been created. And in the interest of time, me not typing this analysis prompt for the agent here, I'll just paste it in and ask it to do the analysis. Like I said, I've uploaded my genetic sequencing data. I'm hoping you can help me understand what my risk of developing Alzheimer's disease is, know that it can be influenced by certain genes, and how this compares to reference samples from both healthy individuals and those that were diagnosed with Alzheimer's disease. And based on this data, I asked the agent to give me a detailed assessment. Now, the agent, you can see here, actually recognized my personal gene sequencing sample that I just added to my knowledge bank. And it also found a bunch more reference gene samples. We can see here all of these knowledge assets that we recreated in these two genomic data databases. So this is now available to the agent, and the agent does this risk assessment based on the available and verifiable data on the private samples and the reference samples that are made available for research. And we can see here it analyzed my genetic profile, compared it with reference samples, and provided risk assessment based on all of the data that it had available is verifiable and can be traced back to its origin. So provided risk assessment, provided conclusion, gave me some moderate risk assessment for developing Alzheimer's disease and some general recommendation. Of course, these are fine-tuned and improved, but this is a quick showcase of how an agent could be using private personal gene sample data along with the data samples, genomics data coming from, in this case, two, but of course, European Union-wide connectivity of genomic data repositories and achieving those network effects where personalized healthcare AI agents would be able to access the private sensitive data that we can actually have a look at how this looks in knowledge graph form, similar to the reference samples that we uploaded, but this one is of course ours and private. The agent, the potential is in expanding from just two genomic data repositories to something going across the European Union, expanding the amount of samples and genes potential that the AI brings to personalized healthcare. That's a quick showcase. Hope you enjoyed it, and thank you.